In section 10.4, we're going to take that same 6-step hypothesis testing process that we've learned in the previous 2 sections and apply it to the variance or the standard deviation. And I say variance or standard deviation because it's the same method for both. What happens is the hypotheses here are going to change depending on whether you're using sigma, which is standard deviation, or sigma squared, which would be the variance. Now keep in mind, just like before, just like all the other ones, they have some rules. Namely, your sample has to be from a simple random sample, and it has to be from a population that is normally distributed. All right. Same steps. You still got to find a test statistic. It's a different formula for that test statistic. It's right there. And then you have your classical method or your p-value method. Since this is using the chi-square distribution, you can tell that because that test statistic is the chi-square statistic we learned in 9.3, I think it was, section 9.3. For the confidence interval for standard deviation, which means you're going to need the chi-square table or technology to find those critical values. Critical values are always the hardest to find. The p-value method's the easiest because that's the one that StatCrunch does with like no problem, or a calculator. All right. Down here we've got to make our decisions. Again, the classical method's more difficult, and we state our conclusion. So let's look at this. The GRE is a test required for admission to many U.S. graduate schools. Student scores on the verbal reasoning portion are said to have a population standard deviation of 120 by the company that makes the test. You don't believe them and you want to test that value. So you collect a random sample of 10 scores. Their values are below. So the first thing I did was I made a normal probability plot. Now, why is that normal probability plot an important graph to have in order to be able to conduct a hypothesis test of the standard deviation? Well, in order to perform a chi-square test, we need to know that our population is normally distributed. We were not informed anywhere up in the instructions that it was normal. It doesn't say it anywhere up here. And our n is really small. Our n is only 10. So that's not good, right? So we have a small n. We don't know our plot is normal, or our data was normal. But this plot shows us that it is normal. It comes from a normal population. Therefore, we can conduct our hypothesis test. All right, now what is the sample standard deviation? For that, well, if you're tricky, you can notice that it's right up here in the mini-tab output 105.4. Or you can go to Excel, and you can type S over here. Oh, and I put this 10.4 example 1. I typed up the numbers. And then I just kind of labeled it. S is equal to the standard deviation. And again, I have new Excel, so it's stdev.s for me. If you have old Excel, it's just stdev A2 to A11. There we go. There's our standard deviation. It doesn't really have to be there. I can put it anywhere I want. Alrighty, so that's S. That's our sample standard deviation. Our sample size, that's pretty obvious, that's 10. You can tell it with the count feature if you really want, equals count of A2 to A11. And it'll tell you there's 10 in there, right? Oops. There we go. Alrighty, done. Now, look at our formula for the test statistic. So you can see it's chi0 squared n minus 1 s squared over chi0 squared, or excuse me, sigma 0 squared. What is the statistical name for s squared? Where have we seen s squared before? And the answer is we saw it in section 3.2. It's called the sample variance. And sigma 0 squared is the population. How about this? It's the null. Here, it's the population variance according to the null there we go, hypothesis. So according to the null hypothesis, sigma squared is a certain value, right? Whatever you set up to be in your null and alternative hypotheses, that's what you assume to be true unless you can prove it otherwise. So the s squared is the sample variance. The sigma squared is the population variance, at least as far as you're concerned. Now, is there sufficient evidence to conclude that the standard deviation is different from 120? Use the classical method. Now there's two ways you can set up your hypotheses, and I just want to make sure it's clear to everybody. So you can say, okay, standard deviation is different, not equal to 120. So your null hypothesis is that it's equal to 120. Your alternative is that it's not equal to 120. So that's a totally valid way to do this. Now the other way you can do this, you could write it like that, or you could write it as sigma squared equals 14400. Now where am I getting that from? Well, if you take 120 and you square it, you get 14400. That's what it is. So that's where I got that number from. Because if the standard deviation is not 120, then the variance is not 14,400. They go hand in hand. So you could write the one on the left, or you could write the one on the right. Either one is completely valid as your null hypothesis. Okay? An alternative hypothesis. Now, alpha they gave to us, they said it was 0.05, so I'm going to write 0.05. I don't have to write the symbol alpha, by the way. I could just say at the 0.05 significance level, and you'd still have to know that that's alpha. All right, now what about chi0 squared, or chi null squared? So that's n minus 1 s squared over sigma squared. So you say, okay, that's 10 minus 1, which is 9, times 105.446, that was our standard deviation squared, divided by 120 squared. And you can use a calculator or whatever, and you should get around 6.949. Or you'll see in a minute when we use StatCrunch, StatCrunch also calculates it for us. All right, now the hard part. If you're doing this the classical way, we're going to have to find our two chi-square statistics. So let's figure out a few things over here on the side first. First of all, your degrees of freedom is 9. Since the sample size was 10, right, degrees of freedom is 9. Now, alpha was 0.05, which means alpha over 2 is 0.025. Don't forget, right here, this is what we're looking at. Oops. Right there. Alpha over 2, alpha over 2. So we need chi alpha over 2 squared and chi 1 minus alpha over 2 squared. Those are the two values we need. So I need to figure out both of them. So I figured out that alpha was 0.05, so alpha over 2 is 0.025, and 1 minus alpha over 2 is 0.975. Now, to get these values, let me scroll back up so you can read it. Either you're going to use technology or we're going to use the chi-square table. Let's go grab the table first just for the heck of it and see how it looks. So the chi-square table is down here. We want the 0.025 column, and we want the 9th degree of freedom. So it's 19.023 right there. And then we want 0.975, and it's 2.7 right there. Let's also double check how to do it with technology for the fun of it. We could find it, let's find it with Excel. I think it's easier. Well, actually, it's kind of just as easy as StatCrunch. StatCrunch is also simple. Let me grab that. Go to Stat, Calculators, chi-square. We want our degrees of freedom to be 9. We want our area to be 0.025. Compute. There it is, 2.7. And if you want, you can take a snapshot of it. Well, even if you don't want, take a snapshot of it and say, let's see, this is 10.4. Example 1A. Okay, we got that one. And then to get the other one, you need 0.975. Compute. Now notice it's the opposite of what the table does, because the table does the right-hand ones. So if you want what the table does, you got to go 0.025. Hey, look, it's 19.023, right? So that's the other way you can go. Hold on, 0.3, example, oh no, 10.4, example 1B. All right, I'm going to go back here to my results, and I'm going to copy and paste these in. So copy, just for the heck of it, I'm going to paste them. I'll paste them down here, because I want this value, I want this area up here for something else later, for when we run the test. So that's one way to do it. Honestly, StatCrunch is easier even than Excel. You don't even need to know a formula for it. That's how awesome it is, right? So you just grab your calculator and as in the StatCrunch calculator, stat calculators, pick the chi-square and go with it. All right, so I've got the other one. There they are, copied and pasted. right? So I can see the two critical values are 2.7, 19.03. That's how to find them with technology. That's fine. That's good. And then, hold on. So we did that. We found those two critical values either with the table or with technology or both. And now we have to make a decision, and we are not going to reject the null hypothesis. The reason being because our chi-square statistic, which is 6.949, is in the middle of this white region. Remember, we only reject if it had been higher than 19 or lower than 2.7. In the critical regions, in other words. But we are not in either one of those locations. We're kind of smack dab in the middle. Here. Let's see, 6.9, is this 2? So that's like 15. So 6.9 is like there somewhere. Wherever it is not nearly far enough away to make it worthwhile to reject. Right? So you only reject if you were lower than 2.7, or higher than 19. All right, so since we did not reject, then we would say there is not enough evidence to support the claim that the standard deviation of GRE scores is not 120. Done. Now, let's redo this with the p-value method, and let's also have StatCrunch do some heavy lifting for us, because StatCrunch is a lot easier than all of this. If we don't have to use the classical method, I wouldn't use it, right? Because the computer does, and actually the calculator as well, do the p-value methods with hardly thinking about it. Now, the thing about StatCrunch is the one thing that's a little strange for variance is that it only does variance. It doesn't do standard deviation. So you have to pick variance, pick one sample. We actually have data this time because we had a list of data. If you didn't have that, you'd say with summary. But we have the data right there. It's the GRE verbal data. So click on that. Say next. Now, this is where it gets a little tricky. Now, notice it says the null variance, not the standard deviation. So even if you wrote the 120, oops, right there. Even if you used this hypothesis test set up on the left with the 120, that you cannot use that in StatCrunch. That's the one thing about StatCrunch, is it uses variance only. So we have to make this one the one that we type in. So it's 14400. So 14400. That is my null, that the variance is equal to that, and then my alternative is a not equal. So I'll leave it on the not equal sign, and I'll click calculate. Swing. And you can see right there, there's the sample variance. That's what 105.446 is squared. So if you took 105.446 and squared it, you'd get that. Your degrees of freedom is 9, just like we said. And there's your p-value, and there's your chi-square statistic. See that? 6.949. I'm going to copy and paste right in there. Love it. StatCrunch is just fabulous for this stuff. It's way simpler than doing the classical method by hand. All right. Okay, so you can see your p-value is 0.7152. Think about that for a second. 0.7152, which is really high, which means we are not going to reject the null hypothesis. And actually, I've drawn it for you here. There wasn't a two-tailed test in the pictures for the p-value method. Here, let me go back up. It just had to do with, I get these pictures from the author of the book, and he just didn't draw one for that section because he's not expecting you to do it by hand. But that's okay. You still need to draw a picture by hand just to have a sense of what's going on. So if you draw this picture right here, you can see that's where the 6.94 whatever comes from. Hold on. There's the 6.95, a little bit further over than where I drew it. And there's 9.92. Don't worry about that. You don't care. The only part is that you notice that there's two tails because it's a two-tailed test. And the p-value for both tails put together is 0.7152. So we do not reject the null hypothesis because that p-value is much, much higher than our alpha. All right, so that's how to do it by hand. I'll meet you back here for reading computer output. See you then.